So I have started recording, so you just put in your attendances. Now, yes, you can ask if you have doubts.
So that A alpha, what we had taken that X alpha plus iota or Y alpha, but we are writing in the equation that 2t, sorry, it will be X alpha dot plus IY alpha dot because dimensionally, the, so
Now, what do
sorry,
you mean? So, if I wrote A alpha equals X alpha plus I times Y
yes,
alpha, right?
yes,
Uh,
sir.
and then I showed that Z alpha alpha, which was essentially A alpha dagger, uh, M A alpha, and it was essentially X alpha transpose M X alpha plus Y alpha transpose M Y alpha, right? So
So,
after,
the kinetic energy we have written, the first term is 2t, 2t dash, and second term is 2t double dash. But in kinetic energy there is formula like x dot xi dot and to x j dot. Derivative of first coordinate. I mean, so, uh,
yes, but okay, perhaps you are confused because so 2t is equals x dot transpose m x dot. That's what you are saying, right?
yes, sir. Yes, sir.
So
So,
this x dot is a velocity matrix, right? So this looks like
yes, sir.
uh, a column matrix, then the matrix M, and then this matrix. Okay. So this, so I did not say that what are the values of x dot. What I essentially mean that when M is sandwiched between such matrices, such two column matrices. So when M is sandwiched between such two column matrices, okay, suppose the velocity matrix is like 2, 5.69, and here also 2, 5.69. Okay. So the numerical values are not important. I am just asking that this structure will return me a positive definite quantity.
Okay,
You
okay,
understand?
sir. Got it, sir. Got
Okay.
it.
So
Okay, sir.
this is, so it has the same structure, and that's why it's a positive definite quantity. All
Okay,
right.
sir. Got it, sir.
Sir,
Thank you, sir.
Mhm.
sir,
Yes.
actually the chat box option is not showing in
Chat
my.
box option is not showing.
For me, it's not showing.
Actually, I think from Konal Sengupta, I received that he is present. Devankan, he is also
Yes,
present.
I am able to see the chat box.
No,
Sir,
sir. Even I
It's not
cannot see the chat
visible
box.
for us. Okay.
Okay, I do not understand that. Can you just someone can just log out and re-log in and then please check? Because for some of you it is working at least.
sir, I have left the meeting once and joined again, but then it's also showing the same problem.
Uh,
Sir, it is showing Q&A option instead of chat.
chat and view. I think yes, I have allowed everyone to chat. I think from my end, I am, yes, I am allowing everyone. Then I don't know what is happening. Anyways, so don't worry about that. That's fine. If you cannot write in chat, it's okay. This
It's
class I
okay.
can take as an exception. That's fine. People who can write, you just write. All right. Any other questions from the last class or maybe class before?
Hello, yes, sir.
Yes.
Sir, can you please discuss the homework 2 problem? Second question of homework.
Second question of homework 2. I mean the invariance of Lagrange's equation
Yes, sir. Yes.
under point transformation.
Yes,
Uh,
sir.
okay. So what part you want to be discussed? That like how the mathematical steps or the
Uh,
implications?
Sir, actually, I don't even get how to start the solving problem.
How to start in solving problem? I mean, you do not understand what is meant by that problem?
Yes, sir. Yes, sir.
Okay, the problem. So the problem actually tells you this. I mean, okay, since you have problem, I will solve that problem later. When I come to Hamiltonian, I have plans that I will revisit that part again. So the problem as it is given, suppose you have some old coordinate and some new coordinates, and the new coordinates are expressed in terms of the old coordinates. Okay. So this is Q is your new coordinate, and this is your old coordinate. So for example, if you and actually you can invert it to write q equals q of qt. So this is the inversion of that. So for example, many people have done that. You suppose you are in a two-dimensional polar coordinate, sorry, Cartesian coordinate, and you convert it to polar coordinate. Okay. So then r will be equals to square root of x square plus y square, and theta would be tan inverse y by x, right? These are your new coordinates. So you can call this one your q1, and this one is your q2. These are the new coordinates, and these are the functions of the old coordinates. So this small y and small x. So this is can be taken as a q2, small q2, and this is your small q1. Okay. Now, so and the new coordinates are related as a function of the old coordinates. So this is basically a function of the old coordinate. Okay. So now you see the connection between this and this. Okay. So I have a set of old coordinates and I have a set of new coordinates, and the new coordinates can be expressed as a function of the old coordinates. So first you see an example of where this transformation might be relevant. Hello.
Yes, sir.
Yes. So then the question is, suppose the Lagrange's equation is satisfied in terms of the old coordinates, that is when x and y. So you have this del L del x dot minus del L del x equals 0, and d dt of del L del y dot minus del L del y equals 0. So suppose, so the basically what I am saying is the Lagrange equations are satisfied in the old coordinates. Okay, so that suppose you have proved somehow. Now I am asking, what is the guarantee that the Lagrange's equation will also be satisfied in terms of the new coordinates? So given these two are satisfied, what is the guarantee that this will also be satisfied? So these are the new coordinates. So the Lagrange's equation in terms of the new coordinates. Okay. Now the answer is that if the Lagrange's equations are satisfied in terms of the old coordinates, and the old coordinates and the new coordinates are related by relations like this, which in general are called point transformation, because you are transforming the coordinates of a certain point in space, then you can check that if Lagrange's equation is satisfied in one of the coordinates, then it would be satisfied in the other coordinate also. Okay, so you do not have to rederive the Lagrange's equation in terms of the new coordinates. You know that that will be satisfied. So you have to show that explicitly. So that was the problem. Do you understand the problem now?
Yes, sir. Yes.
Okay, so this is what you have to show. And so the notations are general, so that it is applicable to everywhere. and try it again. And so just give it a try. Even if you submit it late in the homework, that is fine. Okay, but just try it. And later, when I talk about canonical transformation, I will revisit this part again. And if then anyone has problem, I will sketch the solution.
Sir,
Yes.
so in the homework 3, like there are some topics which we have not studied. Like some of us have not studied in EMT or electrodynamics. So can we like submit those questions sometime later after the deadline, which is on Monday, I think.
Well, you can do it, but I'm not sure if those will be covered in your electrodynamics class at all. Okay. So if it is not covered, do not use that as an excuse not to submit those. Okay. But if you want, you can submit it late. I do not mind, at least you try. But I mean that problem set, the homework number 3, is particularly designed for people who wants to venture into the field of theoretical physics. Okay.
So can you just like give us some references to studies to study those particular topics?
Oh, there are plenty of good references for such electrodynamics things. Okay, so what I suggest is the standard book is the book by Jackson. Perhaps you have been recommended this book already, but for personal reason, I am not a big fan of this book. But everyone reads this book, so give it a try. And for this relativistic electrodynamics, actually, so I mean electrodynamics is always relativistic, and the tensor notations, you follow the book by the proper chapter by Landau-Lipsis. Okay, this is another place you can start. Okay, and so these are two good references, and there was another for the electromagnetic field tensor. There is a book. So this is an old book, but nevertheless, it's a great book. But for the first timers, the notation would be a bit weird. Okay, the book by Panofsky and Phillips. Okay, so this is a book on electrodynamics that I liked very much. But I think the problem is so every time you encounter an expression, all these mu 0, epsilon 0, and c, it plagues this thing. So that's why you get, when you study electrodynamics, you first of all get used to something called the Lorentz Heaviside unit. Okay. So Lorentz. So if you express your electric field and magnetic field in this unit, then you will see that this mu 0, epsilon 0 does not enter in your expressions. Okay, these are all 1, and c is equals 1 also. It's the first step towards natural units. So this book and this book, they do not use Lorentz Heaviside, so they just use usual SI units. But I personally do not like to keep track of powers of C. Okay, so that's why I use this unit. It's called the Lorentz Heaviside unit. I don't know if it has been introduced in your electrodynamics course or not, but get used to that. Perhaps I gave the homework problem in this. If you do not use it, this unit, then you will have mu 0, epsilon 0 flying around everywhere. Okay. But to do homework 3, you do not have to consult any book. I mean, in general, for electrodynamics and FMU, you can consult other books. But it's a straightforward homework. You have to just sit down and calculate. I have given every hint there already. So I already told you what is AMU. For now, you just assume that what I am telling you is correct. Okay, and I have already told you what is JMU. Okay. Now you have to basically compute F mu nu, and F mu nu is given by del mu A nu minus del nu A mu. Okay, so and mu nu runs from 0 to 3, right? So mu equals 0, 1, 2, 3, and nu is so on. Okay. So first thing you notice is that if mu nu is antisymmetric, so the diagonal terms would be 0. Okay. So for example, if 0, 0 is 0, and so on and so forth. So it's a 4 cross 4 matrix. The diagonal entries will be 0. I want you to calculate the off diagonal entries. Okay. So if you calculate the off diagonal entries, you will essentially find here perhaps Ex, Ey, Ez, the electric field components, perhaps here minus Ex, minus Ey, and minus Ez. Okay. And here you will find, I think, this is xy, so it's Vz minus, I am guessing this, so don't take my words for it, but something like this. So I need you to find first of all this F mu nu as this one. You explicitly calculate, you use your formula for E and B, you should find this. Okay.
Okay, sir.
Yeah, and then the rest is straightforward. You just so this is a practice of how to do tensor summation, how to explicitly do tensor summation. Okay, and you get used to these languages, and then we'll talk about. Okay, so then similarly, this thing F mu nu, you calculate this whatever this is, and then you calculate F mu nu tilde. And you see there are no uncontracted index here. All the indexes are contracted. So these are usually called scalars. Do you know about these scalars, vectors, tensor of rank 2 in your from your mathematical physics courses?
Yes, sir.
Yes, just very basic.
Yes, so learn about that. So these are scalars. Scalars means that they do not transform under your coordinate transformation. Now, what is the coordinate transformation for this for relativity? It's the Lorentz transformation. So these quantities do not change under Lorentz transformation. Okay. The idea is whatever you find it here, it would be invariant under Lorentz transformation, and that would be extremely useful in guessing some results. Let me give you some flavor of electrodynamics that perhaps you have not thought about in your courses. So if you calculate this stuff, F mu nu, you will get E square minus B square. Okay. Some constant, maybe 4 times or 2 times, I do not remember. I think it's 4 times. I do not remember. And this, if you calculate, is it will be E dot B. Okay. Again, minus 2 times E dot B or something like that. Okay. So first of all, you calculate that. Now these things, what are these? These are my Lorentz scalars. So these are the quantities that does not transform under the Lorentz transformation. Okay. And now perhaps you have already realized that electricity and magnetism cannot exist independently. They are connected. And the connection is special theory of relativity, or the theory of relativity in general. Why I say this? So suppose you are, so the standard example people give is that suppose if you are holding a stationary charge, an electron, on a platform of a train station. Okay. So with respect to you, the charge is stationary. And what you have, if you want to find the electromagnetic phenomena at a point P, okay, in space, what you have, you just have the electrostatic field, which is basically Q by R. Okay. So is that correct? This is the thing. So you have the electrostatic field, this Q by R, right? Now, for a person who is on a train, who is moving, who is on a moving train, the train is moving in that. So with respect to that person, this charge is moving in the opposite direction with respect to that person. Okay. Now the thing is, uh, mm, with respect to that person, the moving charge is equivalent to a current, right? It's some kind of a current. It's not an uniform current, but it's still a current. Okay. So that current, so it will have an electric field because there is a charge. So at the point P, with respect to this person on the train, there would be an electric field as well as a magnetic field. Let me call it E prime and B prime, and the train frame is S prime. Okay. Now you notice that this electric field and magnetic field are not Lorentz invariant quantities. They change under the Lorentz transformation properties. Okay, they change under Lorentz transformation, right? So if you go to a different Lorentz frame, you go to a different inertial frame, you get different values of E and B. So this electric field and magnetic field, these statements are frame dependent. Okay. Now what is so now you might ask, so if what you have you have just electrostatic field in one frame, which is this, and you have E prime and B prime in another frame, you know this E is equals Q by R, then what can you tell about E prime and B prime? Actually, you can solve exactly for E prime and B prime, but the solution is, let's say, complicated. Okay. The thing is, but even if you do not do the complete solution, you can say many things about this E prime and B prime. How do you say this? You look at these two things. These are standard tricks actually, and for competitive exams, these are the questions you might expect actually. So you look at these two quantities. Remember, whatever be the value of E and B, these two quantities are Lorentz frame invariant because so if you calculate E square minus B square in this frame, and it would be equals to E prime square minus B prime square first of all, and if you calculate E dot B in this frame, it would be equals E prime dot B prime in the other frame, because these are my Lorentz invariant quantities. Now I already know when I have pure electrostatics, so my magnetic field is 0. So the left hand side is 0. So even if I have E prime and B prime, I know that E prime dot B prime should be equals to 0. That means these E prime and B prime would be mutually perpendicular to each other. Okay, how nice. Okay, so whatever that E prime and B prime be, this would be mutually perpendicular. Otherwise, this will not work. You can also say in the in the in the old frame, my E square minus B square was greater than 0. So in my new frame also, E square minus B prime square should be greater than 0. That means magnitude of E prime should be greater than magnitude of B prime. Okay, so these kind of things you can already say without doing any calculation if you remember these quantities. Okay. Also, how does E prime, so given E in a certain frame and B in a certain frame, so in this frame I have E equals Q by R and B equals 0. And what would be then E prime and my B prime? The exact formula can be obtained by this thing. Okay. So you know, since F mu nu is my rank 2 tensor, so F mu nu will transform like this. So you can say that F alpha beta prime, say let's in another frame, it should be given by your metric tensor first of all. So I think it's lambda alpha mu lambda beta nu F mu nu. Okay. So suppose you know F mu nu in the old frame. So in the old frame, the F mu nu would be, so you substitute Ex, Ey, Ez, and these V's are 0. So you know F mu nu in the old frame. You know the Lorentz transformation matrices because you know with how much velocity the train is moving, and then you calculate your F alpha beta prime, and in the new frame you just calculate what is your E prime and B prime. So it's an easy way of calculating E prime and B prime in the new frame of reference. So I want you to practice these kind of things. Okay. So if you get used to this language of tensor, the calculations, in my opinion, becomes easier and more intuitive. And that's why I think you should get used to these languages. Okay. Any further questions, or do you understand why this might be important? You get a feeling at least.
Sir, what if tilde mu nu suppose that
Oh, so f tilde mu nu is called the dual of f mu nu. It's a bit. It's a bit. So
So it's epsilon, alpha, beta, 4 indices, and that F mu mutants.
yes, so I defined it actually already. So f alpha beta tilde is basically, I mean, if you calculate f alpha beta tilde and you express the four components, you will see the role of E and B are interchanged. So E comes here and B comes there. Okay. So you do that, then you will find out what it means. So it's defined as epsilon mu nu alpha beta f mu nu. And this epsilon mu nu alpha beta is the completely antisymmetric tensor of rank 4. Okay. Now, the physical meaning, so we call it mathematically, we call it the dual of the this tensor f mu nu, but it has some interesting thing. Okay. So there is a symmetry called the CP symmetry. Let me not guess, not CP, this is just called it P. Okay, so it's parity, let's say it's parity. Okay, so so basically under parity, this F alpha beta is odd, let's say. Why do I call it odd? Because parity in a sense like transforms your your like inverts your coordinates, right? So the idea is okay. Let me come from here. So let me give this example. So this E square and B square, the magnitude of a vector is always a parity even quantity. Okay, so if you invert your axis, E square and B square does not change. Okay, but I don't know if you remember that if uh, E is a proper vector, but B is a pseudo vector.
Yes, it comes from a Carl losses.
Yes, and essentially that. But then you have to assume that A is a proper vector, but that's fine. But it's basically it's the cross product of two proper vector. If you remember Biot-Savart law, is the cross product between R, the current, and R. So this is basically a cross product of two proper vectors. If you change your things, then it changes. So this is a proper vector and that is a pseudo vector. So the dot product between these two should be a pseudo scalar. Okay. So so the this thing is it gives me a pseudo scalar. Okay. And so but f mu nu, so that's why we call basically f mu nu tilde to be the parity conjugate of f mu nu, because if you take the dot product you get some sort of a pseudo scalar that does not transform under parity transformation. So if you want to think about this way, then it is that. Okay. And there is a more sophisticated analysis in quantum field theory where these kind of things are usually called um, the CP odd scalar. So there is symmetry, charge conjugation symmetry, which is similar to parity. So let me not get into that. Okay. So let us say that this is related to some discrete symmetries in nature. We can understand certain interesting properties about nature by looking at terms like this. Okay. And so this is why f mu nu tilde is important. Okay. So people who will be doing say theoretical physics can learn more about that. We can discuss it later, I guess. Anything else? Okay, so let me now come back to my original agenda, which is classical mechanics. All right, so my classical mechanics, what we left at was that, so we found out the properties of omega, and we found out that omega alpha square is real and positive, of course. Now, so the master equation from which we obtained that, if you remember, we wrote an equation something like this: omega alpha square minus omega beta square. So omega beta star was here, but now I am removing the star because now I know that omega alpha square is real. So A beta transpose M A alpha. So this was my master equation. So now, what I noticed that for alpha not equals beta, when alpha and beta are different, that is to say this omega and this omega are different, then what you have is the multiplying thing, A beta transpose M A alpha. This should be equals 0. Now this is kind of the property of the orthogonal vector on the so in just the difference is there is an m in between. So A beta and A alpha is such that A beta transpose M A alpha equals 0. Okay, so it's some sort of an orthogonality relation. So let me write a sort of an orthogonality relation. Okay. But that does not uniquely fix my A beta or A alpha, because I still know that this thing, the magnitude of A alpha, which I mean is some sort of a magnitude, is still a positive quantity. So this Z alpha alpha, I proved it to be real and positive quantity. Okay, so this is sort of magnitude of the vector of the vector. Now, so to write it in a nicer form, so this Z alpha alpha is arbitrary in general. So what I define now, I now define called the normalized eigenvector. So A alpha bar, which I define as A alpha divided by square root of Z alpha alpha. So it's like dividing by the norm. So if I do that, then I have A alpha bar transpose M A alpha. This would be equals 1. Okay, and I already have this to be equals 0, and this just readily translates to, even if you divide by their magnitude, is A beta transpose M A alpha equals 0. Okay, so these are the things. So kind of an orthonormal combination. Okay, so these things together can be written as, I can concisely write these relations as A alpha bar transpose M A beta equals delta alpha beta. So this takes care of my convention of normalization of my eigenvector, so as to say. So this is the first thing, that is how you conventionally write your A alpha. Okay. So these normalized so-called eigenvectors are very efficient in expressing certain things. So first of all, I want you to notice that just like this, this relation, I can also sandwich eta in between A alpha transpose and A beta transpose, and I get another interesting relation. So if I do this thing, A alpha transpose eta a beta. So if I need to, sorry, a beta, this, if I need to compute the value of this thing, then first I notice that this part, so eta times a beta, should be equals to, from the main eigenvalue equation, you go back to your main eigenvalue equation. So this part would be omega square m a beta bar. Okay. So now you are basically multiplying this with a alpha transpose. So this is being multiplied by a alpha bar transpose. Okay. So you can write it as omega beta square a alpha bar transpose m a beta. Okay. So this is again delta alpha beta. So this is omega beta square delta alpha beta. So if you sandwich eta between a alpha and a beta, you get omega beta square delta alpha beta. So we can use this relation, which I call equation 1, and this one, equation 2. We can use these two relations to define something called the normal coordinates. So now I come to the normal coordinates class. Okay. So the normal coordinates. So the normal coordinates would be defined as, so if I define coordinate which I call xi alpha, okay. So xi alphas are defined as this. So your usual coordinates, this is your usual coordinate, the xk that we had written, is equals alpha equals 1 to n, okay, a bar k alpha psi alpha. Okay, so I define, so this is my definition of the normal coordinates, of course, for k equals 1 to n. Okay, so you invert this equation and to get your xi alpha. But if I do that, then what I have, oops, then what I have is this. So if I write down my potential energy in terms of the normal, in terms of the usual coordinates, it was half jk eta jk xj xk. Okay, and that should be equals to half summation over jk. There will be two summations, and summation over alpha beta, because xj and xk would be replaced using this. So let me write it down first. So suppose I replace xj as summation over alpha a bar j alpha xi alpha. Okay. And similarly, I replace xk as summation over beta a bar a beta xi beta. Okay. So you can write this thing here as eta jk, then a bar j alpha xi alpha, then a bar no k beta xi beta, right? Okay, so now if I write v equals half, I interchange the summation. So first I write summation over alpha beta, then I take out xi alpha xi beta, because these things does not depend on the summation over j and k, so I can take this product out. Now I have this summation jk. I write it in a particularly intentionally I write it as in a nice form. So a bar j alpha eta jk and a bar k beta. All right. So so this is the thing. So now if you notice, this summation is essentially in the matrix notation it will be given by a bar alpha transpose eta dot a bar beta. Okay, so this is precisely the this summation gives you. Okay, so using that you can write V alpha would be summation over half alpha beta xi alpha xi beta, and this summation here is just omega beta square delta alpha beta, if you remember, omega alpha square delta alpha beta, doesn't matter. So this means that it will force alpha equals beta, and you will just be left with summation over alpha omega alpha square xi alpha. Sorry, xi alpha square. There are two xi alpha. So this is my potential energy. Okay. Now in the same way, I wanted to show that the kinetic energy, which was basically half sum over jk mjk xj dot xk dot, terms of my generalized velocities. If you calculate everything, so this would be equivalent to half alpha then xi alpha dot square. Okay, so just show it. Okay, and it will go in a very similar fashion as the as this thing, as the calculation for potential energy. Okay, now now if you write your Lagrangian, so the Lagrangian, which is equals t minus p, this would be equals to summation over, let me take out summation over alpha first of all, and then half xi alpha dot square minus half omega alpha square xi alpha square. Okay, so this is alpha equals 1 to n. Now this is quite remarkable. So you compare it with the Lagrangian of a simple harmonic oscillator. Okay, so the Lagrangian of a so what I write is that compare it with the Lagrangian of a simple harmonic oscillator, which is given by half equals in one dimension half m x dot square minus half m omega square x square. Okay, so if I take mass equals 1 for unit mass, I just write it as half x dot square minus half omega square x square for unit mass. The oscillator has an unit mass. So I see that my Lagrangian is precisely this, and it is basically the sum of n number of such oscillators. Okay, this is the sum of n number of SHO, sum of n SHO. The remarkable thing is that all these simple harmonic motions are disentangled because there is no cross term, there is no xi alpha, xi beta. So all these things are disentangled. Okay, so by defining, by moving from x to xi, so by moving from x to xi, okay, we have kind of disentangled the motions, and we have expressed it as, so expressed it as n independent simple harmonic motions with, in general, different frequencies. Okay. So this is the advantage of going to the normal coordinates. So if you want, then you can have if you define your normal coordinates, then in terms of the normal coordinates, all your simple harmonic motions are disentangled. And then, yes.
So what is meant by disentangled?
So by disentangled, I mean that there are no cross terms between, so there is no mixing between xi alpha and xi beta. Okay. So I mean that suppose you have two coordinates. So suppose you had originally you had x1 and x2. Where did my, wait a minute, for some reason my, yeah, I got it. Suppose you had your coordinates say x1 and x2, and you had in the Lagrangian you had terms that were mixing between x1 and x2. Suppose you have coordinates x1 and x2, then remember, in the original Lagrangian, your Lagrangian would be, so L equals m11 x1 dot x2 dot, maybe half, okay, plus m12 x1 dot x2 dot. Here there is no half because there are two terms, m12 and m21, plus half m22 x2 dot x2 dot, then minus again half eta 11 x1 x1, or rather x1 square, minus eta 12 x1 x2, minus half eta 22 x2 square. So this is your original Lagrangian, right, in terms of x1 and x2, because it's eta. So but in terms of xi1 and xi2, this will look like this, and this just look like half xi1 dot, sorry, this is not x2, this is x1, half xi1 square plus half, so rather I can write half xi1 square minus half omega 1 square xi1 square plus half xi2 dot square minus half omega 2 square xi2 square. So xi are the coordinate which basically get rid of terms like this. Not only that, it also immensely simplifies your mass becomes 1. Okay, and that's why you move to. So this is what I mean by disentanglement. So here there was a coupled term between x1 and x2. Okay, so 1 and 2 are not disentangled, but in terms of the normal coordinates, the motion in the one direction in the normal coordinate and motion in the two directions are independent of each other. That is what I mean by disentanglement. Is that a bit clear?
Yes, sir. Got it.
Okay. Any other questions?
Sir,
Yes.
sir, by using sir, if you try to solve this by using equation of motion, just using Newtonian concept, and then we there find that a sine term by using the the Taylor expansion, we neglect all the terms and we'll take just theta term there, just for small oscillation. Can you find like this and that and that is at this point?
Where at which point? So after Taylor expanding, we got this. So this is, so we wrote this precisely like this term was written on the ground that I am neglecting higher powers of x's. That's why we wrote it.
Yes, sir. So I didn't understand that we are finding using this Lagrangian, but we can easily do by using Newtonian mechanics. Then which one will prefer, sir? This I mean, sir, this Lagrangian process or the Newtonian process, sir?
See, when you have a coupled oscillation, when you have this entanglement between x1 and x2, then uh, x1 and x2 does not individually undergo simple harmonic motion. Okay, so what I mean by, so when you have the Lagrangian with such mixed term, the usual coordinates are mixed, then x1, x2, these things, they do not undergo SHMs individually. So they are basically linear combination of those two. Suppose there are two different frequencies, then the solution of x1 would be some let's say c1, then then let's say c1 times e to the power I omega 1t plus c2 times e to the power I omega 2t. Okay, when I did that. So you see, this is not a pure SHM. It's not a pure SHM. It is a superposition of two SHMs. Okay. So the usual coordinates, your standard coordinates, if they are mixed like this, they do not undergo a simple harmonic vibration. Then what are the coordinates that undergo simple harmonic vibrations? Okay. So those coordinates are these x's.
Okay, sir.
Do you if you have further confusion, let me know. Okay. I mean, where this will be important, if you ask that, the answer is very simple. The immense importance it gets in terms of solving molecular dynamics. If you want to apply quantum mechanics, let's say. So suppose I give you this Hamiltonian, or this Lagrangian means like this Hamiltonian, and I ask you to solve the quantum mechanics of this one, say Schrodinger equation corresponding to this one. You will be in a total puzzle. How to solve it? How do I go about this x1, x2 term? I have never encountered it. It's a two-dimensional problem. I do not know how to solve it. You are stuck, right? You have to do special tricks. But then you know, if you move, if you redefine your coordinates, say x1, x2, if you redefine into xi1 and xi2, then it breaks into two independent simple harmonic vibration. So basically, in terms of xi1 and xi2, you solve your quantum mechanics, you get your energy eigenvalues. These are two independent harmonic vibrations. So one quantum number is n1 and another quantum number is n2. One frequency is omega 1, another frequency is omega 2. So you have solved in terms of xi1 and xi2. Now at the end of the day, you revert back to your x1 and x2 just by this relation, and you solve for x1 and x2. Where did I define my normal coordinates? So you revert back. So if you have found a solution for xi alpha, you revert back using this ak alpha to your usual coordinates, and that's your solution. So that's how it makes our life easier if you want to. So that's why it always helps if you can disentangle your equation of motion into a number of simple harmonic vibration. And simple harmonic vibration is well tried and tested. We know how to handle it. And if I can break down, if I can completely break down my my motion into a number of independent simple harmonic vibrations, I am basically done. So that simplifies a lot our picture, and that's why we use normal coordinates to analyze stuff. Okay. I mean, if you have not encountered this thing, just think about this problem, okay, and how would you do it, and then you will have a better idea. Suppose I give you one Hamiltonian, okay, so half 1 by 2m px square plus py square, okay, and this is a two-dimensional harmonic oscillator problem basically. And I give you, say, I can make things more complicated, but let me start with a simple example. So half m omega square, then x square plus 2xy plus y square. Okay, and I ask you to find out the energy eigenvalues of this system. Okay, so this is a two-dimensional problem, and you try to find out the energy eigenvalues for this system. And if you try solving it using just writing down your two-dimensional harmonic oscillator, you might not be so lucky. Let's say you will be in trouble. There is a trick basically. So let me see if you can get this trick here. So how would you solve this problem in quantum mechanics? So if you get that, if you understand how would you solve this problem, you perhaps understand what I mean by normal coordinates here. Okay, just for fun, try that. Yeah.
Can we take it like x plus y as a single?
Exactly, you have to take that, but in general also. So here,
I can
basically,
write it in terms of A transpose M A,
So
and A
we
will
can
be
take
1
x
1
plus y
1
as
1.
the coordinate. I think. So
well, you have many ideas. Just try. Okay,
Okay, sir.
just try.
Sir,
You
in
have
the
to.
quantum mechanics, we have
In
to
the
solve this.
yes, it's very simple. It's very simple. It's essentially a one-dimensional
Then
problem.
we will first find the solve for omega squared.
No. You are perhaps not getting the point. So what I mean is that you have to do a coordinate transformation. So the coordinate transformation is an orthogonal coordinate transformation in this case. So suppose if I define xi x equals 1 by root 2 x plus y, and xi y equals 1 by root 2 x minus y. Okay. So this is an orthogonal thing, right? So you can easily check that again. Xi x dot would be 1 by root 2. I think you have another class right now. So you just try this and write in these in terms of xi x dot and xi x y dot. So what you will find is that this basically reduces to p xi x square pre xi y square plus, I do not know, here might be half m omega by root 2 whole square, if I am not terribly wrong here, and then just xi x square. So here you have, so you take these two pieces and you see that this is a simple harmonic motion here, and another simple harmonic motion is this, but with omega equals 0. There is no omega there. Okay, there is no quantization there. That's a free particle. So this is the only quantization you get. Okay, just try that. This is a standard problem. Okay. So these kind of coordinate transformation, you are moving the coordinates so that your potential looks simple, is in essence what you trying to do here in terms of normal coordinates. That's what we always try to do. So we always try to map our unknown complicated problems into a set of known problems. Okay? So that is what is your normal coordinates are doing. Okay. So all right. So I think I will stop today's class here. I think I do not want to overshoot. Okay. So if I can take maybe one quick question, if there is a burning question right now. Okay. So let me stop recording for now.